Okay. The second one says that the power of this estimator, our estimation of the gradient, noisy version of the gradient, should be smaller than some constant multiplied by the norm of the gradient. So what it says that the norm of our noisy version should be more or less comparable with the norm of the actual gradient. Okay? It can go to infinity. If the actual gradient goes to infinity, that's fine, but they should be on the same level, more or less, determined by this C0. Okay. So very general assumptions that almost always holds. But then we do need them, at least these parameters, for the convergence establishment. And then finally, there exist two scalars, m and mv. I should change the notation, probably go with a small case m and a small case mv. Okay, but then there are two scalar here that satisfies this. The variance of our estimator is smaller than some constant. Again, the variance can grow large and can go to infinity, okay? Because this term can go to infinity. This is a constant less than infinity, positive but less than infinity. This is positive, but then that guy can go to infinity. But this tree says that if we are close to the optimal solution, in that case, this gradient vanishes, actually. Okay, so the second term here vanishes. So if we are close to the optimal solution, then we cannot go so much wrong. So we can have a bounded error, bounded variance, determined by this m. So here you can see that this m plays a bit of role everywhere. So if m grows to 0, then it means that we can go wrong as long as the actual gradient is high. But as soon as the actual gradient of the function vanishes or starts to vanish, then our variance of the error can decrease and decrease and decrease, okay? So this is a good strategy here you can do. So you can try to develop some g function here whose m decreases as the actual gradient decreases as well. So essentially you can say that, okay, whenever at the very beginning I just don't care about what is the variance of my gradient estimator or my noisy gradient, but as soon as the actual gradient becomes smaller and smaller, I try to make a better estimation of that gradient, okay? Better estimation means m should go to 0. And then in that case, you can just shrink the radius of that ambiguity ball. Okay. From these two, you can show that this term, we have seen that here. So this term will be lower bounded by some alpha and beta. Alpha is actually m here. And some beta, and then try to find beta. In the next slide, I think that I didn't update that, but this beta in the next slide is called mg. So this is mg in the next slide, and this is m. But then try to find mg. Okay, it's just direct application of these two and definition of this. Okay, so here, just an additional note, the only limitation that we do have to be on expectation on the same half space. So here you can easily apply, if G is in the same half space on expectation, then you can easily multiply that by any positive definite matrix, because multiplying by a PD matrix here wouldn't change the half space. So we can just precondition that by any H that we have seen in some other slides. Okay? So this is the whole idea of going with the steepest descent version of the gradient descent. So the only thing that you need to have is just this inequality. Okay. Then we can actually show that this would happen. And if we do those assumptions, so we do have some assumptions here. So let's try to use those assumptions. So previously we had a box where it says that this expectation would be smaller than something. And if you just apply the assumption that I just showed, then you can show that that something would be smaller or equal to that, and then it's going to be like this. Again, we're going to have the blue term and the red term, and here everything is even more clear. So it says that in every iteration, you can have a linear improvement. This is actually a linear improvement. Okay? So you can have a linear improvement determined by this factor here. And at the end of the day, once this term vanishes, then you can have some ambiguity ball here that you cannot go anywhere better than that. But then how we can prove this? It's just a direct application of a star. So it's just replacing this guy And then noting that this is, let's say this is mg, and this is, you can show that this is actually this m. So just replacing this inequality, well, this inequality here, and just rearranging the terms. You can just show. You will first come to this guy, and then you can show this guy just by rearranging. And then using the second inequality that I have shown, instead of that, just replace that with this, and then everything would follow. So that's easy. Sure.
So here we assume that the estimator is unbiased, right?
The estimator, let me see. Yes, here the assumption is that the estimator is unbiased because we have this term here. If the estimator is not unbiased, then we can, so essentially we started from this guy here because it's unbiased. But then if it's not unbiased, then instead of having this term here, you're gonna have the actual gradient transpose the average of our estimator. And then you cannot go to this because you have another things in the second term, and then you cannot factor these two out to have this convergence here. It's gonna be just a bit more messy in that case. So the first convergence result, from now on, you're gonna see a lot of convergence results, but don't be scared. You can find some of the proofs here in the appendix slides, but then I can point to the references where you can find all the proofs anyway. The whole idea of having them is not to show how you can prove them, it's just to get those insights and then how you can play with those parameters to run your stochastic gradient version. So the first theorem says that it is actually for a strongly convex f and fixed step size. So essentially it says that if you have a fixed step size that follows this inequality, just to remind you, the same inequality that we had for gradient descent, what was it? Do you remember? So for gradient descent, we had that alpha should be 1 over L. That is the inequality for the constant step size that we need to have for deterministic gradient descent. So if we do have that inequality for a step size, and if we meet that, then the expected optimality gap would satisfy this inequality. And the way to prove is just starting from this and doing some basic algebra that you can find in proof. But the whole idea is that, so you have a linear convergence. So this is the definition of linear convergence, right? You had an exponential, so you have this term, and then you can, if you want to convert to the e to power something, then use 1 minus x smaller than e to power minus x things. And that inequality to recover from this guy, e to power something, or vice versa. The whole idea here is says that just ignore this first term. The expected improvement or the expected convergence is linear, but unfortunately, you are not linearly converging to the optimal solution. You are linearly converging, just move that here, then you're gonna have something smaller than something to power k minus 1, the same thing here, right? So you're linearly converging to that ball that I have mentioned. So that is the whole idea here. And then what would happen if, unfortunately, you choose some bad hyperparameters? For instance, just ignore m of g and ignore c. Just assume that they are just 1 because they can be really 1. And so in that case, alpha should be between 0 and 1 over L. Okay? So in that case, what would happen if you have an overestimation of L? So this is exactly your homework 2A. Try to estimate this L for some data sets and some real problems. But what would happen, and then there I asked to go with a small L, as small as possible. But why? Because to have this alpha as large as possible. But then what would happen if you have an overestimation of L? Then the step size is going to be much smaller, and the convergence rate going to be much smaller first due to this. Here in alpha, just assume that alpha is 1 over L, right? So the convergence rate here is going to be much worse if you have a bad L. But unfortunately, if you have an overestimation of L, also here you can destroy this guy here as well. So you may be able to, unfortunately and unintentionally increase the radius of that ambiguity ball. So then you would not be satisfied by the optimal solution, and then you say that, okay, why I cannot run this on this problem, whereas I was able to run this on some other problems? Simply because it could be due to just a wrong estimation of L for your specific problem. As easy as that. So this is what I said, and then what would happen if G is an unbiased estimator, then this bound holds, of course, but then you may assume that for some cases C is 1. What was C again? Sorry for coming back again, yeah, fourth. So C was here, your choice, and just assume that you are choosing your class of estimators so as this is greater than some C1. And then you can easily choose MG to be 1 for MG is this guy, and then you can easily show that MG can be 1. So in that case, you can recover the things that I have mentioned. You can retrieve alpha between 0 and 1 over L, that we know. It's still, everything is really depends on your choice of L, how you're going to estimate that from your data. Well, not estimate, how you can find out that. That's a better word. OK, cool. So this is the convergence that we have seen. I just put this guy to the left-hand side, and then you can see that we have this term here and this term here, and the linear convergence rate to that term. OK, so the first item says that the fast convergence, actually linear convergence to a neighborhood of the optimal value, and let's call that neighborhood an ambiguity ball. And the optimality gap is this term. This term is the radius of that guy. We have a contraction factor, which is this guy. This is called contraction factor as well. These kind of algorithms, you can show that this algorithm is trying to solve a fixed point iteration, if you know that. And then this is a contractive mapping, just some other equivalent words. So in that case, this is called contraction factor here after k iteration. Okay. Then a simple modification is as follows. What we can do is that, okay, so let's look at that. Let's play with alpha here. What is the role of alpha here? What will happen, let's say, if we reduce alpha to half? Then the first thing is that if we look at this term, or let's say this term, contraction factor, if you reduce alpha to half, and if you use first order Taylor series of this guy, then you will see that alpha linearly increases this term here. So it has a linear role here, almost a linear role here. So essentially, if you reduce alpha by half, then you are doubling the number of iterations that you're going to need to recover the same term here. Just assume that this is like capital M, and use first order approximation of Taylor here, then replace alpha by half of alpha. Then to recover the same M, you're going to need twice k as previous. Okay? So it says that essentially, approximately, if alpha step size is half, then you're going to need twice iterations. Okay, to have the same convergence, to converge to the same point almost. But, so this is a bad side. On the positive side, if you reduce alpha, then we are linearly reducing this radius of ambiguity. So then one can say, let's do this. So let me see if I can draw something here for you. Okay, so let's say this is k, and this is E of f of wk plus 1, something like that. Okay. This guy, with some alpha, we're going to converge to something like this. Okay, and this term here is actually this term here. Okay, so this is the radius of ambiguity ball. We're going to converge to somewhere here, and then we cannot go anywhere better. In some iterations, depend on the iterations, we can go inside, we can go outside, but on expectation, we're going to be around that ball. So this is the expectation, so we're going to converge to some point here. But then we can run another algorithm exactly from the same starting point, but then that algorithm going to converge much slower, but can, let's say this is for alpha. What would happen if we run this algorithm with half of alpha from the first starting point? Then it's going to look like this. It's going to converge much slower, actually. But then it will converge. Well, this is not a good picture. But then we can understand that it can converge. It will converge to somewhere here, but at a much slower rate. So definitely it's not a wise choice to start with this half alpha. So this corresponds to half of alpha. It's not a wise choice to start with that because it's going to destroy your convergence time. So what you can do, and this is usually what people do in practice, is start with some alpha, pretty good choice of alpha, which gonna be C divided by LMG. So the maximum alpha that you can choose, because alpha should be within 0 and this guy. Okay? So choose the maximum one, see when the iteration stalls. So essentially, you can't have an expected improvement. Then afterward, switch to this guy. Then what would happen from here, you're going to start. So from here, you're operating with alpha. From this point, you're going to start from half of alpha. Then you're going to stall after some other iterations. Then you again half alpha again. So that's going to be alpha 4. And then by that very simple algorithm, you can really converge to the optimal solution. Why the optimal solution? Because ultimately you are saying that this alpha should grow to 0, right? So this radius grows to 0, then you can recover the optimal solution. But what is the cost here? The cost is the excessive number of iterations, right? Because you're going to need a lot of iterations to do this operation anyway. OK, cool. Still, just recall that by playing with alpha here, we didn't reduce the variance of the gradients noise. So we didn't play with that at all. The only thing that we played with is, let me show. This M, essentially, well, M divided by C anyway, but then just assume that this M is the variance of your gradients noise, your estimator. We didn't play with M at all. We only played with this alpha. But later on, we can see that there are some even better ways to play with M rather than alpha. OK. And then by that, it's actually not that much easy, but intuitive to show that the effective convergence rate is going to be, again, order of 1 over k. If you do this halving of alpha, then you can recover the convergence rate of the gradient descent. Think about that. The whole idea behind is to show that after every iteration, the number of iterations that you're going to need here, the number of iterations is comparable to the number of iterations here, comparable to the number of iterations. So the thing is that per iteration, you do have a very small computation, but you need a lot of these form of iterations. Okay? And then you can see that the convergence is going to be almost in the same order of 1 over k if you do that. Okay, think about this. Cool. You know what does it mean? It means that this is the convergence rate of a gradient descent. So you're going to recover somehow indirectly the convergence rate of a gradient descent. A strongly convex function and diminishing step size. In previous slide, we had fixed step size. Here we have diminishing step size. That should follow some rules, strange rules like this. But then you can show by induction that if that's true, those rules, then you have a convergence which is nu divided by something plus k. So essentially for some constant nu, then this is 1 over k, essentially, something of that order. Remember the convergence here, which is linear to some ball. But then here, you will actually converge to the optimal solution at its sublinear rate, okay, with 1 over k. And just usually for most cases, the first term here, this is the denominator of that term. The first term here is the dominant factor usually. Okay, so really don't be worried about the shape of the second term. Just look at the first term here. Okay. So one thing that's very important here is that the whole convergence rate is a function of L and M. Okay, cool. And then the choice of beta. And what is beta? Beta is 1 over mu c, and mu is the strong convexity parameter. So again, if you have a bad estimation of the strong convexity parameter, you can destroy the whole things by just changing. You can destroy the whole things by just, and then alpha 1 should be smaller than the same things that we have seen before. So if you have, again, an overestimation or underestimation, very bad estimation of your parameter of the functions, L mu, then you can destroy this step size. And then, of course, there are some other better ways. There are lots of papers on that, how to choose those step size more intelligently. But I'm just saying that if you don't do them, and just choose some random step size, you can really destroy the whole convergence of this guy. It can go on and not converge at all. So whatever I'm saying here will be somehow illustrated here. So let's compare two things. The first one is mini batching. with NM. So you may wonder, is it wise to go with mini batching with a subsample of size NM, or go with the stochastic gradients and then doing update based on just one gradient instead of NM gradients? If you look, so this is only for constant M, not diminishing size M, alpha M. But if we look at that, then we're going to have these two inequalities. So if you have mini batching, so actually I should have put that in the previous two slides before. But then if you have that, then with mini batch of constant alpha, alpha should be small here for these intuitions to hold, or the things that I'm saying to hold. But if you have a mini batch of size nm, then that sigma 2 that you have seen, sigma 2 would be sigma 2 divided by nm. So the m that you have seen is going to be m divided by nm, because the variance of the noise is reduced here. So the whole idea here is to have a smaller constant size alpha divided by nm. Okay, so the thing is that here, the variance is smaller. The variance is m divided by nm. In this case, because we have a mini batch. Here, just to compare that smaller variance, we are just playing with alpha. So we are just reducing alpha to alpha divided by nm. Then you have alpha divided by nm here and alpha divided by nm in that equation here as well. So this is the role of nm here. Then why we are doing that? Just to make them comparable. So this is nothing but this equation here. I'm just playing with that equation here. Why we did that? Because we want to achieve the same convergence to the same ball. And then we want to see which of them are better in terms of the rate of the convergence. Shall we go with mini batch, with constant step size, or with stochastic gradient, with one gradient, but then higher number of iterations, or a smaller constant? Then you can see these two, and then you can write down the first order Taylor approximation of this guy, and then see that essentially the number of iterations are almost the same. So the amount of work that you need to do, work means computation, that you need to do is almost the same in these two. So here you need more iterations here. Many more iterations means that the k here, to have the same term, if you want to keep this guy equal to this guy, k here should be nm times k here. You can show that by approximating this guy by first order Taylor. So what it says that it depends on the way that your server works and how much access you do have to parallel optimization or not. The amount of work anyway would not be so much different in these two. Okay, so these are just equivalent anyway. Well, almost equivalent. Two other results which are a little bit different. I'm just showing that because previously we have seen only this. Now we can see convergence in probability as well. And then in order to be able to go from this guy to this guy, you should use something like Markov inequality. Okay. This is from Boyd, I guess. And then some additional notations, we have seen them so far. So this is the norm of this error should be bounded. We have seen that, which is called Lipschitzness, Lipschitz continuity. And then this guy is the bounded norm of the initial guess, the bounded error for the initial guess. So if you do have them, then you can show that we can have this convergence for diminishing a step size and convex F. But the good thing with this is that this holds actually for subgradients method. So that's why that I said it here. You can just replace the gradient with subgradient, and then you can have this convergence bound here. For this to hold, alpha k should follow a square summable but not summable step size. You know, these famous things. So the summation of alpha k grows to infinity, but then summation of alpha k square would be finite. And then you can recover that, and then you can see the proof there. From here, you can have a convergence of this, where the probability of this guy that you are looking for, because anyway you are not looking for the expectation, you are just observing this guy. But then probability of this guy being larger than some threshold would be smaller than some arbitrary chosen delta. Using this and Markov inequality, you can show that this does hold. Okay. But almost the same convergence rate again. Then this is the last one. Again, I'm just showing that to show you that once we talk about the stochastic approaches, there are lots of many definitions of the convergence. So this is another definition of the convergence, and in this definition, we show that f evaluated at this point would be very close in expectation to the optimal solution. And what is this? It means that once k increases and increases and increases, then we spend more and more, increasingly more time around the optimal solution. So this is the meaning of this term. Because just imagine that after some points, wk be close to the optimal solution, right? That this guy would be very close approximation of the optimal solution, and this f evaluated at that average point would be close to the f star. So this is the meaning of that. At times goes, at k grows large, then we're going to spend more and more time around the optimal solution. So this is the meaning of this. And then again, you can say that if mini batch size reduces by a factor of nm, if you have a mini batch size of nm, you can reduce this sigma here, and then you can reduce this guy here again. Again, same results. Different proof anyway. I'm going to skip this. Just saying that for non-convex, we cannot show finding the optimal solution, but we can show converging to some points that we will be satisfied with. For instance, this guy says that we're going to converge ultimately if this guy grows to 0, as the same we can see. This guy says that we're going to spend more and more time around the points where the gradient is going to be smaller and smaller. So this is the meaning of this. We cannot say that where the gradient is small if it is minimum, if it is maximum, or if it is saddle point, because for all those points, gradients can grow to 0, can vanishes. But then here, the only thing that says that it will converge to some of those points. Okay, so this is the only thing that here we can say. But still, this is great news because we can run that and then we can converge to something. So this is better than nothing. Okay, you can just read that, and I'm skipping this one as well. But then think about the proof of that. You can use those inequalities. It seems hard, but then you can use those inequalities actually to show that. This is the same idea that you can play with alpha k to make sure that you are spending more and more time around the areas where the gradient is actually 0. Because this guy grows to 0, so then this guy should go to 0. It means that, but then this is the summation. So you're spending more time around where the gradient vanishes. So this is the whole idea from here. So ultimately, you cannot stay bounded away from 0. So this is not 0 from the gradient 0. So this is the whole idea here. The only thing that you can show with non-convex, well, not the only thing. This is some food for thought. Think about them. I'm not going through them. We're going to use the last point a lot in lecture 5. So think about all of them. Okay, so the last part is about variance reduction techniques. So everything that you have seen so far is mostly 1970 or in that order, but then the thing that you will see here, they are mostly 2010 plus, and really active field of research in these variance reduction techniques. Okay, so there are different techniques to do that. The first one, again dating back to so long time ago, and then you will see that in the food for thought slides, is increasing mini batch size. As you have seen, you can increase that to be able to reduce the variance of that estimator of the gradients. You can reduce the step size alpha to reduce the radius of the ambiguity ball. It's not so much variance reduction of the gradients, but it's still, you can call it variance reduction a little bit. At least it can help to converge to the optimal solution. But then finally, the things that I will talk about in the next 2 slides or 3 is mostly based on this very simple rule that you will see. So the thing is that you can always do this very simple trick. The trick is as follows. If your random variable is like x, and if you know another random variable, let's call it y, and you know the expectation of that y, okay? What you can do is that you can define a new random variable as a function of alpha, which is alpha x minus y plus e of y. And then you can show that the expectation of this guy, if e of y, of course, this is an unbiased estimator of this guy anyway, right? So what you can show is that the expectation of e of z gonna look like this, okay? And the variance gonna look like that. So what happens if alpha is smaller than, if alpha is 1? Then you have an unbiased estimator. So Z is an unbiased estimator of X if alpha is 1. Okay, so there is a way with alpha to control alpha to make it an unbiased estimator of X. But what would happen if Z is a biased estimator for some alpha? Alpha should be between 0 and 1 in this case. So in that case, if alpha is smaller than 1, then you can show that under some choices for Y, the variance of this guy can be smaller than the variance of X. So what happens is that you intentionally make a biased estimator by using this. Again, remember that the underlying assumption is that there is another random variable Y for which you know the expectation of that random variable. Somehow somebody will give you this. But if you know that, then you can just create this Y and this Z and then try to iterate instead of on X, iterate on Z, because now the variance of Z is smaller than variance of X. So this is the whole idea here. And the main idea of this SVRG from 2013, stochastic variance reduced gradient, it's mainly based on 2 iterations now. So generally speaking, if you remember stochastic gradient main frame, it's just 1 round of iteration. So there is no inner loop or outer loop. Whereas here we do have 2 loops, inner loop and outer loop. In the outer loop, we're gonna find that expectation of Y that we have set. So just remember now that our X is W, the main parameter that we want to estimate, but instead of optimizing over X or finding the optimal parameter, we're gonna find the optimal Y. So actually that should be Z anyway, but that's okay. But we're gonna find this guy, and then this guy is W tilde, and this W tilde, in order to be able to run here, you need to know the expectation of this guy. Expectation of this guy will be given here for you, the things that you're going to need. So you will find that in the outer iteration. In the inner iteration, you're going to use that here to create that things that we have seen here, X minus Y plus E of Y, X minus Y plus E of Y. Okay, so this is what you're going to find. But then E of Y will be given to you in the outer loop. Okay. So first, it says that compute all the gradients and store all the gradients. Then do that for lots of inner loops. And in all the inner loops, you're going to randomly sample from that set and then run based on this iteration. Okay? The proof, actually the sketch of the proof are there. You can see them. But then with this, you can show that you can recover the linear convergence rate that we had. The linear convergence rate to the optimal solution, not to the vicinity of the optimal solution. You can recover the linear convergence rate, but at which cost? The cost is that first you're gonna need a memory to save this guy first. You're gonna need computation of 2 gradients per inner loop. You're gonna need to compute these gradients and also this gradient. So you should ask worker zeta k, which is 1 worker. You should ask that to find the gradients at this point and find the gradients at this other point. Okay, this is your X and this is your Y. Find the gradients at these 2 points. Compute this difference here. So 2 gradients per inner loop and 1 memory. And by the way, in outer loop, we're gonna need to compute all the gradients and store all the gradients. So just recall that. And this is fundamentally different from stochastic gradient when there is no such a step to compute all the gradients. Okay, this is more like gradient descent kind of things where you can access to all the gradients. But then here you can go with the linear convergence rate, and there are tons of extensions of this guy. So this is generally, at least this form is to optimize some f. You can imagine from this that f should be 1 over n summation of f of I, an unconstrained optimization problem. But then there are tons of extensions, how you can extend that for constraint optimization problem, non-smooth problems, and lots of those extensions. You can see them. So this is the basic idea of SVRG. You can see the proof. And then the last slide is something that people are even working today, really. And then this is SAG, stochastic average gradient. This is a bit more similar to a stochastic gradient kind of nature. But so there is no outer loop or inner loop kind of thing. There's just 1 loop. Okay. But then the trade-off that you need to have here is to add memory here. the whole idea, or the main idea here, is that at some points, gradients, you will compute the gradients of some of those indices, some of those fi. At some iteration, you find those gradients. If you are lucky enough, so this is the main idea. If you are lucky enough, at some other iterations, you're gonna have access to some other gradients. That's okay, okay? But if you are lucky enough, the previous gradients that you have seen from those other machines, they are almost the same now. You don't have access to the gradients right now of those machines, but then if you're lucky enough, the previous gradients that you have observed, they are close to the current value. So this is the main philosophy. And this is the meaning of this guy. So I guess that this is important. We can, okay. Just assume that here it's iteration, k, here. And here I'm just putting gradient of f of 1. For simplicity, I'm saying gradient 1, gradient 2, gradient 3, and up to gradient n. So what would happen is that k1, 2, up to k. At iteration k, just assume that in iteration 1, we're going to find this gradient. Find means that we ask machine 1 to give us this gradient. So we know this guy here. And this is the only thing that we know in iteration 1. In iteration 2, we're gonna randomly select one of them. This is the meaning of this. This is the meaning of this. Just randomly select one of them and then compute this gradient at that point. Okay? At other iteration, we randomly pick some of them. And what would happen at iteration k is that at iteration k, we're gonna observe this one, for instance. But then we don't have any observation for these values, right? So then the whole idea here is just to have a memory, and then in that memory, just recall from the memory. So just recall the exact value from here. Of course, this is not the true gradient at this specific parameter, because just imagine that, recall that this is the gradient of f3 evaluated at, I don't know, wn, for instance, and then this is the gradient of f3 evaluated at wk. So w's are different. So the gradients should be different. But the whole idea is just put that here, and then put that here. And then say that your g, which should be an estimation of 1 over n, summation of gradient of f of I at wk, right? Estimation of this guy. Let's put that as average of all these values. So 1 over n, summation of hat of I. And hat of I is exactly j if you pick that specific index at that iteration. If you didn't pick that index, then go with the last time that you have seen that index, and then just call that guy here. And then by that, you can show, so this is a biased estimator. You can easily show that. This is biased estimator. This is not unbiased. So that's why that the convergence analysis is a bit messy here. But then usually, well, SVRG is biased. It's unbiased anyway. But mostly based similar to SVRG kind of algorithm, and then convergence analysis. And convergence rate is almost the same as that. The good thing with this is that you don't have, so let me recall this guy. So the good thing is that you don't have these compute all the gradient step, but you need to have a memory to save n gradients. Okay. So this is SVRG again, and this is SAG. Okay. So these are the main difference. Convergence rates are almost the same. Analysis pretty much similar, but then different assumptions on these two. And the additional extension SAGA, with essentially what it does, it tries to make these approximation unbiased. So add some more term here, which to make it unbiased, and that's very easy to do. So add to all these terms the difference between these two, and then that's it. You can check that paper. It's not a big deal anyway. So it's just an update of this iteration. Instead of being like that, it's plus something else to make it unbiased. That's it. Convergence is almost the same. Everything is almost the same. Much easier convergence analysis, by the way, due to unbiased estimator. Then what? Okay, by the way, just a last comment. If you look everything like this as a table averaging, how a stochastic gradient behaves here. In a stochastic gradient, recall this iteration, wk plus 1 equal to wk minus alpha k gradient of zeta k, right? So this is ours, where this guy is, let's say, gradient of f of zeta k evaluated at wk, right? This is nothing but assuming that all the, you will, this zeta k, assume that this is the zeta k that you have observed, and then, so you have access to this guy. Assume that all these guys that you don't have access, they are equal to this guy. So you don't know what is the value here. You just assume that estimation of this guy is equal to gradient of your zeta k, which, by the way, doesn't have to be like that at all. But just assume that this is the case. So put for all these parameters, for all these gradients that you don't observe at iteration k, the things that you have observed. Then do the same thing here. Then you're going to have your g, which is an estimation of 1 over n summation of gradients of I, which is 1 over n summation of gradients of I, individual estimation. And individual estimation, for all of them, replace the one that you have observed here. So it's going to be 1 over n times gradients of zeta k, right? And then you can recover this iteration here. So it's really dumb to say that just observe one gradient and assume that the gradients of all other functions they are all exactly identical to the gradient that I have observed from that one specific function. But this is the way that it works. Question?
What is the probability of not observing these gradients at specific state?
Here, the probability is 0. So the question is if it is possible, by the definition of these iterations, that we don't observe any gradient at all at some steps. It's not, because the way, in that case, we don't do the update at that iteration. So we just remove that k. Because here it says that sample zeta k, so there should be some zeta k. If due to some communication error or whatever, we cannot get the gradient at that step, then definitely you can define something like effective number of iterations, where the effective number of iterations is smaller than the actual number of iterations, because you're going to miss some of those iterations, updating some of them. And then do the updating based on this effective number, and then all the convergence result going to be a function of that effective number of iterations, I guess.
So it really depends on the network that we are running down. Gradient isn't on that, because we just I understood it like this, that we divide this and send it to each of our nodes, and it computes and then send it back to master node. And if my network has a high high error rate, and I don't get these gradients, then the probability of missing these gradients increase. So maybe this method won't work very long.
So the question is, what would happen if we run, just to summarize, what would happen if we run these form of stochastic gradients, or even the full gradients, on some faulty network? So running a decentralized version on some faulty network. And then the answer is, we cannot run. So because we need to have somehow the gradients to be able to do the update. So in that case, we're going to need a lot of other tricks, like many things from communication and coding theory to improve the robustness to those errors. Even we need to resend some of them. It depends on how you can deal with those faulty networks. So here, the underlying assumption for everything is that there is no fault in sending those things. But then, of course, you can just generalize and then do reevaluate or recharacterize the convergence rate for those kind of underlying networks. And that is essentially what we're going to do later in lecture 5. OK, you had a question.
Back to the previous the average.
Oh, OK.
No, this one. The average gradient over all of your FYs.
Mm-hmm.
In common machine learning, you kind of assume that is some kind of average over the actual. I mean, all of these FYs is on your data points and yada yada. I mean, like, does that necessarily have to be the total gradient, or can you take a sample of your do several subsamples, so say that the average gradient there is actually the average of some half of the data set, and then you do that on that half of the data set, and then you can do this whole thing recursive, or like why does it
So the question is, can we replace this guy instead of finding 1 over n, which means running that for full gradients? Is it for full data set? Is it possible to subsample the data set and then run this with that subsample data set? So have an estimation of this at that value and then try to work with that. That was the question, right? And then does it working or not? Yes, it works. Well, it depends. I can't really guarantee that it works on all scenarios because the convergence proof of this, at least the first version, is based on that. Why? Because in the proof, there are some expectation of this guy somewhere. And in that expectation, we're going to need these two to cancel out each other. And the way to do that is that the expectation of this guy is exactly this, expectation over the randomness that we do have over zk. So this guy is exactly that. And the expectation of this guy, if zeta k is uniformly sampled, then you can just show that this guy, you will sample. What is the probability? What is the expectation? Expectation is the probability that sampling zeta k, which is let's say, probability that zeta k is I, which is 1 over n, by definition of this uniform sampling. So 1 over n summation of gradient of f evaluated at w tilde k at I. Okay, this is exactly definition of tilde w. So this is just for the trick for the convergence that we need this. But if it is working in practice, if we just subsample that using Monte Carlo subsample, randomly take some samples and then somehow approximate this, I would bet that it can work. The thing is that we know that even if we don't have this, it will work. This is a stochastic gradient things, right? But then the convergence rate would not be as good as the convergence rate in this. So it's just about playing with the convergence rate a little bit. But by the way, whatever we do have here is just theoretical analysis of the bound of the convergence rate, okay? So in practice, you may see a much faster convergence. But then this just says that the rate of the convergence would be upper bounded by some function. But then it won't say what is the actual convergence rate that you would see on this specific data set or the other data set. Okay? So that's it. Now it's time. So there are some references that I have used. I really suggest everybody to read this very nice SIM review. We have already used this convex optimization. This is a very nice foundation and trend book chapter on convex optimization. Very compact but very dense.